Hello guys, today we'll be reviewing topic E.2 in the IB Physics HL syllabus, uh, which is topic that talks about quantum physics. Okay, so first I'll start uh, with what is quantum physics. Well, quantum physics is the study of discrete or quantized particles. It's basically, you could say, the study of small things, very small things actually. Uh, and in order to, and no, this actually quantum physics wasn't around until up until 100 years ago, when scientists began to discover that at very small scales, classical laws didn't apply like it does to big scales. So the only way they could describe these things without breaking the laws of physics were these new laws we'll talk about, new discoveries, all due to the difference between large scales and small scales. On small scale things, um, nature acts differently, and it is also, of course, much harder to observe nature at small scales. So the whole picture is not done yet. Like, quantum physics is still evolving, but we know that quantum physics is a more accurate interpretation of nature than classical physics. Okay, so first I'll start with the most important law in quantum physics. I'll write it down, then I'll explain what it means. It says that E equals hf. Okay, what is E? Of course, is the energy. And H, if you watched my last video, you know that that's Planck's constant, which is a fundamental constant in quantum physics that will come up a lot. And F is frequency, but I'll tell you what frequency we're talking about here. This actually equation let uh, physicists know that actually light light's energy is not made up of its intensity. So if you increase the intensity of light, that does not mean that the energy of the light will become more. No, that's incorrect. It actually uh, says here in this equation that the energy of light is proportional to its frequency. So the higher frequency of light, such as maybe gamma rays, gamma rays have more energy than microwaves because their frequency is much higher. So it here states that the energy of a wave is directly proportional to its frequency. Okay? But here I'll show you another equation, but let's start and I'll try to explain it to you. This actual equation cannot be interpreted using classical physics or classical thinking where light is only a wave. Because if you think about it, a wave is something continuous. It's not made up of small parts, you know? So a wave having that little energy is not true because we use waves for many things. So they came up with a new concept that waves are made up of small packets of energy, we like to call them, called photons. Photons are particles, huh? Particles with no mass. So this is the first interpretation of how waves can actually act as particles. So waves have the wave particle duality, They can act as waves, have amplitude, intensity, these things, but they can also act as particles by this equation. And this equation actually is describing the energy of one photon. So if you get frequency of a wave, any frequency, you are able to calculate the energy of one photon. Okay, so in order to interpret this more, many equations or many things, um many experiments, sorry, were took place. Well, the most important one is Albert Einstein's experiment known as the photoelectric effect. What is the photoelectric effect? So I'll try to draw it here. Basically, there's a metal surface here, okay, any metal surface, connected to wires and some kind of ammeter, voltmeter to measure, and yes, so connected to wires, okay? Einstein now shined a beam of light of certain frequency and certain intensity. So let's draw them as photons here so you could understand. And when these photons or that light struck the metal surface, these photons somehow were caused the emission of electrons. But in this case, we like to call them photoelectrons since the electrons are emitted due to the photons. But the most important interpretation here is that when Einstein, for example, when he had a beam of a certain light and he struck it on the metal surface, nothing was emitted. And when no matter how much he increased the intensity of the light, nothing was still emitted. And this was the most important interpretation, that light's energy has nothing to do with its intensity, rather its frequency. When Einstein increased the frequency but kept intensity constant, photoelectrons were observed and were emitted. So this brought us to this equation. It is very similar to the equation that I showed you above, the maximum kinetic energy of the photoelectrons, since by the conservation of energy, if one photoelectron emits one photon emits one electron, then that electron must have the exact same energy as that photon. Energy cannot be lost here. And that shows how even some laws in classical physics do work on the quantum level, such as the fundamental law of thermodynamics. So it equals HF, which you know, minus phi. So what is phi? Well, each metal has something known as the work function, which is denoted by phi. What is the work function? Well, the work function describes how strongly metal or electrons of the metal are binded to its lattice or binded to the nucleus. Uh, Probably if you take chemistry, you would know that as the number or as the charge of a metal increases, its attraction to the electrons becomes stronger. So in this case, more energy is required to ionize it. And here we are technically ionizing these electrons from the metal lattice. So the more bounded these electrons are to the metal, the higher the work function. And the work function is also equal to HF, but instead of F, we call it F dash. And this F dash is known as a threshold frequency. It's the maximum frequency, or sorry, it's the minimum frequency required for an electron to be emitted. Okay? So we can actually simplify the following equation, that the maximum kinetic energy of the electrons emitted is simply equal to H multiplied by F, the frequency of photons, minus the threshold frequency, which you will be given or not. If they want you to find F dash, they'll give you the F and E, and if you want to find F, they'll give you the other two. Okay? So this equation showed how light acts as a particle, because if you think about it, the emission of electrons shouldn't be instantaneous actually. In waves, in the wave model, the emission of electrons should have been actually took a delay. There's supposed to be a delay between when a photon hit, or wave in this sense, hits the metal and the electron is emitted. But that was abolished when they saw the experiment and how electrons were emitted as soon as these waves or photons strike the metal surface. So um, this experiment, you have to know it. It is the most important experiment in wave particle duality, which I'll talk about more later. It shows how light can behave as a wave, and we'll go ahead and onto the next equation, which is the opposite. It shows how particles can behave as a wave. So particles can behave as a wave, and light can behave as a particle. Thus, we have the wave particle duality. The following experiment is known as de Broglie's hypothesis. So de Broglie's hypothesis states that any given particle that's any given particle lambda has a wavelength described by the following equation. And again, you see Planck's constant again in this equation. It is simply the wavelength of any particle is simply its Planck's constant divided by the particle's momentum, which we could show that it is h over mv. Okay, and this is the equation. But how did de Broglie find out that particles have wavelengths? Well, while trying to hypothesize this wave-particle duality, de Broglie thought of an experiment known as electron diffraction. Why diffraction? Well, diffraction is the most important or the most notable property of waves. As we talked earlier in earlier videos, we saw how light diffracts and creates patterns, constructive and destructive interference. So de Broglie set to diffract an electron through a slit. And what did he find? Well, he actually found a wave, actually found a pattern on the screen. But that pattern you don't need to know, but electrons were aligned in some ways. They're perfectly aligned no matter how they were diffracted. And this showed how electrons can also, specifically you talk about electrons, sorry, because their masses are so small, so the wavelengths are notable. What while um, talking about protons or things like that, the wavelength would be much smaller and wouldn't be as notable, and diffraction would be harder to observe. So here the Broglie wavelength, you probably be calculating the Broglie wavelength of electron specifically, and you know the mass of the electron is given in data booklet. So if you're only given the velocity, you will be able to calculate its wavelength since Planck's constant is also given in your data booklet. Okay, this experiment is the most complex one here. It's not straightforward. I encourage you to actually read about it more, not even the book, but research. But I think in overall that photoelectron effect is more important. But the following uh, experiment and the final one is the most important one in terms of it actually shows how shows the wave particle duality of waves, and it's the most simple one. So what is this experiment is known as Compton scattering. So what is Compton scattering? Well, a scientist named Compton wanted to show how uh, waves or photons were particles. So if you think about particle properties, you'll think about the first thing I think you'll think about is collisions. Particles always collide. So he uh, basically threw some photons at an electron and observed the photons before and after they collide or not after the electrons, and he found out something very important, that the wavelength of the photon after the collision decreased. This made it clear that actually photons did collide with the electrons. Why? Well, let's get the equation we used in the beginning. E equals hf, correct? Right? We can also write that E equals hc over lambda, since f equals c over lambda, okay? So when E decreases, or for a constant, lambda must increases, these both are constants, they do not change, okay? So E decreases, lambda must increase. So when lambda increases in this experiment, that means that the kinetic energy of the photon, or the energy of the photon, some of it has been given to the electron, and the only way that this can occur is that a collision is collisions. Okay, so de Broglie came up with, Compton came up with an equation to show this. But specifically, this equation talks about electrons specifically, since protons and neutrons are too large to observe this. So again, we're talking about electrons. It simply states that the shift in the wavelength or the change in the wavelength, which will be an increase, definitely, is equal to h, Planck's constant again, the mass of the electron multiplied by the speed of light multiplied by 1 minus cosine theta. So this part actually is a constant. You can calculate it. It's known as the Compton wavelength. But the important part here is this 1 minus cosine theta. So if particles, if the photon and electron collide parallelly, so they don't collide because they're parallel, while this will be equal to 1 because cosine 0 equals to 1 and delta lambda becomes 0. But if they collide perpendicularly, while cosine theta becomes 0, and then delta lambda will become equal to this constant right here. And of course, if the wavelength increased at a constant frequency, so the energy will, or no, not a constant frequency. If the wavelength increases, energy must decrease. So in questions, you'll actually be asked to show that energy is decreased. So you'll have the wavelength difference. You'll find the final wavelength and use it back in the equation, E equals hf or E equals hc over lambda to find the new energy of the photon. And you may be asked if the photon has been changed from one part of the electromagnetic spectrum to another. So it was a gamma ray and it became something else. Okay, so now we've talked about the 3 experiments that show the wave-particle duality, and we'll solve some questions. Okay, this is a paper 1 question. Which observation in Compton scattering provides any evidence for the particle nature of light? A. The scattered photon has the same wavelength as the incident photon.
That would be incorrect. Uh, because if wavelength stays the same, that means no collision has occurred. So A is wrong. B. The photon transfers energy and momentum to an electron, causing a shift in the wavelength. Well, that is correct because the equation actually states that there is a shift in the wavelength, so B is correct. Einstein explained the photoelectron effect by proposing that light energy is quantized in brackets called. On this, you don't even need it to be multiple choice, we know it's photons. Okay. Which change would increase the maximum kinetic energy of electrons emitted in the photoelectric effect? So let's write down the equation. E max equals HF minus 4. Increasing the intensity of incident light, like we stated, intensity has nothing to do with the energy of the electrons, rather it has to do with the rate of emission of the electrons or the current, if you want to think about it, since current is the flow of charge. So if you increase the intensity, actually current will actually increase and electrons will be emitted faster, but faster in terms of emission, but the actual speed after emission will always be the same for the sun kinetic energy, so don't get that confused. Using a method with lower work function. Well, this is the work function. This decreases, then Emacs must increase, so the answer must be B. Which of the following observations of photoelectric effect provide evidence for particle nature of light? A. The intensity of one. As soon as you see the intensity, you know what's wrong, so let's skip A. B. Electrons are emitted even at low frequencies if the light intensity is high enough. This is also incorrect, as it again states that intensity is the important factor, which is incorrect. C. Electrons are only emitted when the light's frequency is above a certain threshold. Well, if you read the equation as I wrote it before, yes, electrons will only be emitted, because if this is lower than this, this becomes negative, which is incorrect. There is no such thing as negative energy. So this answer is correct. C. Okay, a light of frequency. Let's write it down. This is a paper 2 question. F equals 8 times 10 to the 14 times the metal surface with a work function of phi equals 2.5 electron volts. If you don't remember, electron volts, in order to convert them to joules, you multiply by E. E is the charge of the electron, which is 1.6 times 10 to the negative 9. Okay, so the next question is asking us to calculate the energy of the incident photons in joules. Well, that is simple. You have the frequency of photons, so you just use an equation E equals HF. So let's use it. It becomes 6.63 times 10 to the negative 34 multiplied by 8 times 10 to the 14. And of course it's in joules, so already. When it becomes equal to 5.3 times 10 to the negative 19 joules. Okay. Number two. Determine the maximum kinetic energy of the emitted photoelectrons. Well, let's write down the equation. You already have everything. But this question is actually telling you in electron volts. So I'll show you how to convert back. So basically we have this. So we have E photon, let's write it as E photon minus 2.5. Since we have the okay, E photon in electron volts is simply this number we got in joules divided by E. E is of course again 1.6 more times 10 to the negative 19 equal to 3.31. Okay, while E max equals 3.31 minus 2.5, which is 5, which would equal to 0.81 electron volts is the maximum kinetic energy that an photoelectron will be emitted if the photon's frequency is 8 times 10 to the 14. And we see that is the correct answer. Light of frequency 8 times 10 to the 4 it shines on a metal surface with a wave function of E. Calculate the Broglie wavelength of an emitted electron. So here he's actually bringing two experiments together. So let's write down. This is a very hard question students struggle with actually, but it's actually very simple. It's simple substitution. So we have the energy of the electron. This is what you use. This is the most important factor. So lambda equals h. Okay. Well, you tell me I don't have P. Yes, you don't have P. I know you don't have P. You only have the mass of the electron, which is in your little booklet, so don't worry. But how will you get the electrons went? Well, it's actually very simple. If you write down the equation for kinetic energy, it's in your little booklet. Actually, you know that P squared over 2n, okay? And you have both of these, So you can simply rearrange for P, and P is simply equal to the square root of 2m multiplied by the kinetic energy of the electron, as substituted in the equation. So the equation becomes lambda equals h over root 2m k, which is equal to 6.63 times 10 to the negative 34 multiplied by this 2m. Let's just write it like this. And this is 9.11 times 10 to the negative 31. And now, the important part is you convert it back to joules. So you're multiplying by E. So it's gonna be 0.81 times 1.6 times 10 to the negative. And the wavelength is 2.8 times 10 to the 15. I think it's something. Oh, I did something wrong. Yes. Forgot to take the square root of the denominator since let's use it to the power of half, which is easier. And the lambda, let's just write the root here. Lambda becomes equal to 1.36 times 10 to the negative 9 meters. And I want you to actually memorize the momentum. That momentum is equal to the square root of 2 times 2m ek, or Emax in this sense. To make it a lot easier to solve these kinds of questions, this question was 3 marks and it's pretty simple. Consider the following changes when monochromatic light strikes a metal So if you don't know, monochromatic light is light of single frequency and wavelength, causing the emission of electrons. Okay, reducing the intensity of the incoming light. Well, we know intensity has something to do with the emission of electrons rather the rate of emission. Lowering the frequency of light that would cause, may cause, may cause no electrons to be emitted based on the threshold frequency. And number three, increasing the work function of the metal that could also cause no emission of electrons. But which of these changes would lead to the emission of electrons with lower energy? So 2 and 3 would work since if frequency is greater than threshold frequency, then it would decrease, then electrons would be emitted with less kinetic energy. So 2 and 3 are the correct answers. Which of the following best represents the concept of wave-particle duality? Light can only behave as a wave, no. Electrons can only exhibit particle characteristics, no. Light and electrons can both behave as particles and waves, and that is the correct answer. From the following experience, you should know that for the photoelectric effect, light exhibits wave behavior, and in the Broglie wavelength experiment, particles exhibit light behavior, and in the quantum scattering experiment, they collide actually, but we talk about light exhibiting particle behavior since collisions are particle behavior. Okay, let's go. Okay, in a neutron scattering experiment, the wave-like properties of neutrons are utilized. A neutron with a mass of 1.675 times 10 to the negative 27 kilograms moves with a velocity of 10 to the 5 meters per second. What is the Broglie wavelength? When you use the equation simply, it's h over p, which is equal to h over mv, which is equal to 6.63 times 10 4. And if you calculate it, the wavelength would be equal to 7.3 times 10 to the negative 9 meters, which is the correct answer. Compare this wavelength to that of visible light and explain its implications for neutron scattering experiment. Well, if you know, wavelength of visible light is actually in the order of magnitude of 10 to the negative 9. So, wavelength of the neutron, the Boyle wavelength of neutron actually lies within the visible light frequency. So what does that mean? Yes, well, this second part of the question is actually not. Yes, you need to know that. Most questions actually are the exact same, they're very repetitive. So we'll stop the video here and thank you.